Alright, we're going to quickly read section 1.3. I wanted to do section 1.3 and 1.4 in the same video because section 1.3 is super short. It actually would have been better to put section 1.3 just at the tail end of the section 1.2 video, but the section 1.4, I have a specific example and specific sort of tangent I want to go down, and that's actually quite involved, and that's going to take a long time to flesh out. I mean, I just wrote the outline, and the outline alone is 5 pages long, so that's going to take a while. Um, I'll probably do other things while I make that. We'll have to see. That's going to take a while. Um, anyway, so let's just read section 1.3 really quickly, and then this will be enough of Artin until I finish the argument. Finish writing out the argument about a cool way to think about determinants. And actually kind of the more mathematically mature way to think about determinants instead of this very elementary way. We're going to show you really what determinant, I don't want to say what determinant really means, kind of a hint of what determinant really means. It's one of the deepest ideas in mathematics. And it's almost impossible to understand in full. You have to really get a ton of context to really wrap your head around this sort of magical function. Anyway, section 1.3, the matrix transpose. In the discussion of the previous section, we chose to work with rows. So the basic premise of this is literally, okay, the previous section was about row operations, and this section will be about column operations. And the whole point is that, well, if you take a transpose of the matrix, then the rows become the columns become rows, and if you do row operations on the transpose, that corresponds to column operations on the original matrix. So in the discussion of the previous section, we chose to work with rows in order to apply the results to systems of linear equations. One may also perform column operations to simplify a matrix, and it is evident that similar results will be obtained. Rows and columns are interchanged by the transpose operation. Let me make sure I'm recording on the correct mic. Yes, I am. Rows and columns are interchanged by the transpose operation on matrices. The transpose of an m by n matrix A is an n by m matrix. Notice that the dimensions flip, so Mike times November becomes November times Mike. Matrix A transpose, that's how you read this A to the T. A transpose obtained by reflecting about the diagonal. A transpose equals Bij, where Bij equals Aji. For instance, 1, 2, 3, 4 transpose equals 1, 3, 2, 4, right? You reflect around the main diagonal. And 1, 2, 3 transpose equals 1, 2, 3. So a row vector becomes a column vector. Here are the rules for computing with the transpose. AB transpose equals B transpose A transpose. So the transpose of a product equals the product of the transposes in the opposite order. That's important. And I don't know an easy way to see that. It's true. Go watch a linear algebra playlist to learn more. I don't actually remember why that's true, but if you, I think if you do enough mental gymnastics, it's obvious. What's going on? A plus B transpose equals A transpose plus B transpose. So if you, when you add two matrices, that just works component-wise. And so it doesn't matter if you do the transpose first and then add, or do the addition and then take the transpose. You're going to get the same result either way. Same with multiplying the whole matrix by a constant. That's what this equation is saying. This one is, if you do the it doesn't matter if you do the transpose first or after the addition. And then, of course, if you do the transpose twice, you end up back at the original matrix. Using the first of these formulas, we can deduce facts about right multiplication from the corresponding facts about left multiplication. So using this transpose product rule. The elementary matrices, 1.2.4, I'm not going to scroll all the way back up, act by right multiplication AE as the following elementary column operations instead of row operations. With A in the ij position, add A times column I to column j, right? So interchange column I and column j and multiply column I by a non-zero scalar c. Note that in the first of these operations, the indices I and j are the reverse of those in 1.2.5a. So literally all it is that if you want to do column operations, you can just do row operations on the transpose. Maybe the equation to think about is that A times E is equal to E transpose A transpose transpose, right? This take the transposes of these in the reverse order. That's going to be A transpose transpose times E transpose transpose. That's equal to AE. And then the transpose of one of the elementary matrices is, again, a different elementary matrix. And that's it. That's all for section 1.3. Section 1.4 is going to take me a while. It's about determinants, and I have a really kind of cool diversion that I want to talk about, and that's going to take a while to flesh out. All right. I'll see you then. Probably going to work on information theory, because that I can kind of just drill through in the meantime, or maybe do some. I need to do more Erlang videos. Those get way more views than the math videos, which is, well, Erlang's cool, so I'm not gonna. Anyway, thank you for listening. That's all.